What if everything you think you know about the universe is just a fraction of the truth? Picture a cosmic rulebook written in code, filled with laws so strange and powerful they bend reality itself. Laws that remain hidden from our everyday perception, yet shape every moment of existence. These aren't just abstract ideas. They're the invisible threads weaving together the fabric of space, time, and even consciousness. And today, we're about to crack that code wide open. Think about the last time you stood under a starry sky, feeling that humbling sense of wonder. What you were really witnessing was the surface of something far deeper, a universe governed by forces we're only beginning to grasp. Dark matter, an enigmatic substance that outweighs everything we can see, yet leaves no trace. Quantum particles that communicate instantaneously across vast distances, as if space and time don't apply to them. These aren't science fiction. They're real, measurable phenomena that hint at a reality far stranger than we've been taught. And here's the thrilling part. Understanding these hidden laws could change everything. This journey isn't just about unraveling cosmic mysteries. It's about rewriting what's possible. Imagine tapping into the same principles that guide galaxies and subatomic particles, unlocking technologies that seem like magic today. Healing energy, even the nature of time itself could be transformed once we decode these universal secrets. Over the next 30 revelations, we'll explore the astonishing truths that science is just beginning to uncover. From the mind-bending behavior of black holes to the eerie connections between consciousness and the cosmos, each insight will pull back another layer of the universe's grand design. So if you've ever felt that tug of curiosity, that hunger to understand the deeper rhythms of existence, you're in the right place. Let's begin. What if the solid world around you, the chair you're sitting on, the device in your hand, even the sensation of weight in your own body, was nothing more than an incredibly convincing illusion? This isn't the plot of a sci-fi movie. It's a serious scientific theory gaining traction among physicists. The holographic principle suggests our three-dimensional universe might actually be a projection, like a movie playing on the surface of an unimaginably distant cosmic screen. Think of it like a credit card hologram, flat to the touch, yet producing a stunning 3D image when tilted in the light. But in this case, the hologram is everything, every mountain, ocean, and living being encoded in flickering bits of information on the edge of space itself. The evidence comes from some of the most perplexing corners of physics. When scientists study black holes, they've discovered something astonishing. The amount of information a black hole can hold seems to depend not on its volume, but on the surface area of its event horizon. It's as if the 3D space inside is somehow stored on its 2D boundary. This bizarre finding aligns perfectly with the holographic principle. Even more mind-bending are experiments with quantum entanglement, where particles separated by vast distances instantly mirror each other's states, as if they're just pixels responding to deeper code written on that flat cosmic surface. Here's where it gets truly revolutionary. If the holographic principle holds, it means the universe operates like a cosmic computer, rendering reality in real time based on underlying data. Your consciousness, your memories, the very passage of time, all could be part of this grand projection. Some researchers even speculate this might explain why we can't find the missing 95% of the universe's mass. Dark matter and dark energy could be glitches in the rendering, areas where the code hasn't fully loaded. The implications are staggering. It would mean the search for the fundamental building blocks of reality isn't about finding smaller particles, but deciphering the language of the universe's source code. Yet this isn't just abstract theorizing. The holographic principle could reshape our understanding of gravity, uniting Einstein's relativity with quantum mechanics, the holy grail of modern physics. It might even hold clues to technologies that sound impossible today, like manipulating reality by rewriting its underlying information. Imagine a future where we don't just observe the universe, but interact with its programming layer. The more we uncover about this potential holographic nature, the more it seems reality is far stranger and far more malleable than we ever dreamed. Time might be the most familiar stranger in our lives. We measure it, chase it, waste it, yet fundamentally misunderstand its true nature. What if the ticking clock, the aging process, even the relentless forward march of history aren't inherent features of the universe, but side effects of something far more profound? Cutting-edge physics is now challenging time's very existence, suggesting it might be an emergent illusion, like the whirlpool that seems like a distinct entity, but is really just water moving in a particular pattern. Take a film strip as an analogy. When you watch a movie, motion feels continuous, but you're actually seeing 24 static images per second. Your brain stitches them together into fluid time. Some physicists argue reality works the same way, that what we perceive as time is really a series of nows stacked together by our consciousness. At the quantum level, experiments reveal particles that don't experience time linearly. Entangled particles react to each other instantly, as if no time passes between their interactions, while photons traveling through the vastness of space arrive unchanged, untouched by time's passage. These anomalies hint that time might not be a fundamental layer of reality, but a surface-level phenomenon emerging from deeper, timeless laws. This leads to a staggering possibility. The past, present, and future could all exist simultaneously, frozen together like frames in a cosmic film reel. Einstein's theory of relativity already hinted at this with block time, where every moment is equally real. Your birth, this video, the heat-death of the universe, all coexisting in an unchanging four-dimensional structure. If true, free will takes on a strange new meaning. Your choices would still matter, but the script might already be written. Some theorists compare it to reading a novel. The story is complete, yet turning each page feels like an unfolding experience. The implications ripple through every aspect of existence. Causality, the idea that causes precede effects, could be another illusion. Quantum experiments show particles acting before the events that trigger them, like a glass shattering before it's dropped. Ancient philosophy spoke of time as cyclical, while modern cosmology suggests it might be an arrow emerging from entropy, the universe's tendency toward disorder. But if time is truly an illusion, even entropy could be a shadow of something deeper. Imagine a civilization that mastered these timeless laws. They might navigate reality like editing a film, jumping between moments or rewriting sequences. Time travel wouldn't be about speeding up or slowing down, but accessing different frames of the block universe. Closer to home, understanding time's illusory nature could revolutionize computing, communication, even our approach to mortality. Religions and scientists have debated eternity for millennia. What if they were both right, just describing different facets of the same timeless truth? The more we probe time's illusion, the more reality resembles a symphony where every note exists at once, and the melody is our conscious journey through them. Whether time is real or not, our experience of it shapes everything, which means cracking this cosmic code could change not just physics, but what it means to be human. There's an invisible hand shaping the destiny of our universe, one so powerful it overrules gravity itself. Dark energy, this enigmatic force, isn't just expanding the cosmos, It's doing so at an accelerating rate, as if the universe is pressing harder on the gas pedal with every passing moment. Picture a loaf of raisin bread baking in the oven. As the dough rises, the raisins representing galaxies move apart. But what if the dough suddenly started expanding faster and faster, stretching the raisins until they could no longer see each other? That's the eerie future dark energy might be creating. The discovery of dark energy came from a cosmic surprise. In the late 1990s, astronomers studying distant supernova made a shocking realization. These exploding stars were fainter than expected, meaning they were farther away than anyone predicted. The universe wasn't just expanding, it was accelerating. This revelation flipped cosmology on its head. Gravity, the force that sculpts galaxies and binds planets to stars, was losing a cosmic tug of war against something far more dominant. Calculations revealed dark energy makes up about 68% of the universe's total energy, with dark matter and ordinary matter making up the rest. Yet, despite its overwhelming influence, we've never directly detected it. Here's where the mystery deepens. If dark energy's strength remains constant, the universe faces a cold, lonely fate, galaxies speeding away until their light can never reach us, leaving future civilizations with an empty sky. But there's a more terrifying scenario. What if dark energy isn't constant? Some theories suggest it could grow stronger over time, becoming what physicists call phantom energy. In this nightmare scenario, the accelerating expansion would eventually overpower every force in nature. First, galaxy clusters would be ripped apart. Then individual galaxies, stars would be torn from their orbits. In the final moments, even atoms would be shredded as the fabric of space-time itself is stretched beyond repair. Yet not all hope is lost. Alternative theories propose dark energy might weaken or even reverse, allowing gravity to regain control. Some models suggest it could be a temporary phase, like the inflationary period right after the Big Bang. Others speculate dark energy isn't a force at all, but a sign our understanding of gravity is incomplete, a cosmic illusion created by hidden dimensions, or the way our universe is embedded in a larger multiverse. The truth might be stranger than we can imagine. What's at stake isn't just the fate of distant galaxies, but the fundamental nature of reality. If dark energy is a property of space itself, what Einstein once called the cosmological constant, it could mean empty space isn't truly empty, but bubbling with quantum energy. Some researchers even explore whether dark energy is connected to consciousness, with the universe's expansion driven by the same processes that generate awareness. Whether the cosmos ends in a big rip or continues expanding forever, one thing is clear: dark energy holds the pen writing the final chapter of existence. And right now, we're only beginning to decipher its language. Einstein once dismissed it as spooky action at a distance, but quantum entanglement has proven to be one of the most baffling and revolutionary discoveries in physics. Imagine two coins spinning in perfect sync, one in New York and the other in Tokyo. No matter how far apart they are, flipping one instantly determines the state of the other. That's the essence of entanglement, where particles become so deeply linked that measuring one immediately influences its partner, even if they're light years apart. This isn't theoretical, it's been confirmed in labs repeatedly, defying our everyday intuition about how space and time should work. The implications shake the foundation of reality as we know it. According to classical physics, nothing can travel faster than light. Yet entangled particles seem to communicate instantaneously, as if the universe has a hidden backchannel where the rules don't apply. Some scientists speculate this could mean space itself is an illusion, a kind of projection over a deeper layer where everything is fundamentally connected. Think of it like two ends of a stick. If you push one side, the other moves immediately, not because a signal traveled through the stick, but because they're part of the same structure. In this view, entangled particles might be like endpoints of a hidden cosmic fabric we can't yet perceive. What makes this even stranger is that entanglement doesn't just challenge space, it upends our understanding of time. In certain experiments, changing one particle appears to affect its partner before the change even occurs, as if cause and effect can flow backward. This has led to wild but serious theories, like the idea that time might be a two-way street at the quantum level, or that the future could subtly influence the past. Ancient philosophies spoke of the web of life, where everything is interconnected. Modern physics might be catching up to that wisdom in the most unexpected way. The real magic lies in how this could reshape technology. Quantum computers already harness entanglement to perform calculations that would take ordinary computers millennia. But imagine a future where we exploit these links for instant communication across interstellar distances, or sensors so precise they could detect gravitational waves from the birth of the universe. Some even propose that entanglement could be the key to unlocking faster than light travel, not by moving through space, but by bending the rules of connection beneath it. Yet the deepest mystery remains: why does the universe operate this way? Is entanglement a bug or a feature, a clue that reality is far more interdependent than we ever imagined? From the behavior of subatomic particles to the large-scale structure of galaxies, hints of this hidden connectivity are everywhere. Perhaps the greatest lesson of entanglement isn't just about physics, but about perception. We're taught to see the world as separate objects in empty space, but the universe might be whispering a very different truth, that at its core, everything is profoundly, inextricably linked. What if every choice you've ever made, every path taken or not taken, exists simultaneously in alternate realities? The multiverse theory isn't just science fiction. It's a legitimate scientific framework suggesting our universe might be one bubble in an endless cosmic foam, each bubble operating under completely different rules. Picture a vast library where every book tells the story of a universe with unique physics, some where gravity is stronger, others where time flows backward, and a rare few where conditions are just right for life like ours to emerge. This idea springs from multiple branches of physics. Inflationary cosmology proposes that our universe underwent rapid expansion after the Big Bang, and if this process happened once, why couldn't it happen again and again, creating countless pocket universes? String theory takes it further, suggesting higher dimensions could harbor parallel worlds separated by membranes thinner than a single atom. Even quantum mechanics hints at branching realities. Every time a particle has multiple possible states, some interpretations suggest the universe splits to accommodate all outcomes. You might have turned left this morning, but in another reality, your alternate self turned right. The implications are staggering. If the multiverse is real, there could be versions of Earth where history unfolded wildly differently, where dinosaurs never went extinct, where empires rose that we've never heard of, or where you made that one decision you've always wondered about. Some universes might be so alien they're unrecognizable, realms of pure energy, dimensions where matter never clumped into planets, or even realities where the concept of time doesn't exist at all. This raises profound questions. Are we living in the most probable universe, or just one rare outlier where life was possible? Could there be civilizations in other bubbles communicating across the multiverse, using physics we can't yet comprehend? Critics argue the multiverse is untestable, more philosophy than science, but recent breakthroughs are bridging that gap. Astronomers hunt for bruises in our cosmic microwave background, potential evidence of collisions with other universes. Quantum experiments explore whether particles can leak between realities, and if dark energy's value seems oddly fine-tuned for life, the multiverse could explain why, in an infinite array of universes, some had to get lucky. Beyond physics, this idea reshapes how we see existence. Religions speak of many worlds. Indigenous cosmologies often include layered realities. If every possibility exists somewhere, failure and regret take on new meaning. Every what if is real in another version of you. The multiverse might be the ultimate answer to Fermi's paradox. Alien civilizations exist, just not in our particular bubble. Whether it's a scientific truth or a beautiful metaphor, one thing's certain: the universe just got a lot bigger and a lot stranger. The most shocking experiment in quantum physics doesn't involve massive particle colliders or distant galaxies. It starts with a simple question: does a tree falling in the forest make a sound if no one is there to hear it? At the quantum level, the answer might be no. The double-slit experiment, first performed over 200 years ago, reveals something astonishing. When tiny particles like electrons are fired at a barrier with two slits, they create an interference pattern on the other side, as if each particle passes through both slits simultaneously like a wave. But here's the twist: the moment scientists place a detector to observe which slit the electron actually goes through, the behavior changes. The particles stop acting like waves and start behaving like discrete particles, as if they're aware they're being watched. This is the observer effect. Not just that measurement disturbs the system, but that the very act of observation seems to force reality to make up its mind. Some interpretations take this even further. The von Neumann-Wigner theory proposes that consciousness itself is the trigger that collapses quantum possibilities into concrete reality. In other words, the universe exists in a haze of potential until a conscious mind observes it, like a fog clearing only when someone looks. Think of reality as a grand orchestra playing every possible melody at once, and consciousness as the conductor that selects which notes we actually hear. This isn't mysticism, it's a serious, if controversial, interpretation backed by Nobel laureates like Eugene Wigner. Even Schrödinger's famous cat, simultaneously alive and dead in its box, only settles into one state when someone lifts the lid and looks inside. The implications ripple through every aspect of existence. If consciousness shapes reality, does that mean our thoughts have tangible power? Experiments in quantum biology suggest living organisms might exploit this phenomenon. Photosynthesis, for example, relies on quantum coherence particles exploring multiple paths at once to find the most efficient route, almost as if plants choose the best outcome. Human cognition could operate similarly, with our brains acting as quantum observers, constantly collapsing probabilities into the stable reality we experience. Ancient traditions from Buddhism to Hermeticism have long claimed that the mind and world are deeply intertwined. Modern physics might be catching up to that ancient wisdom. Yet skeptics argue this gives consciousness too much credit. The decoherence interpretation suggests interactions with the environment, not observers collapse quantum states. A dust particle or a stray photon could do the job just as well as a human mind. But even this doesn't fully explain why observation matters. Some researchers propose a middle ground, that consciousness doesn't create reality, but filters it, like a radio tuning into one station out of many broadcasting simultaneously. The most profound question isn't just about physics, it's about us. If the universe responds to observation, are we passive witnesses or active participants? Artists and inventors often describe moments of inspiration as if their ideas already existed, waiting to be noticed. Could creativity be a form of quantum observation, pulling possibilities into reality? Whether consciousness is a cosmic architect or just a curious bystander, one thing's certain: the line between the mind and the universe is far blurrier than we ever imagined. Black holes have long been painted as the ultimate cosmic monsters, insatiable voids that shred stars and trap light itself. But what if we've misunderstood their true nature? Beneath their terrifying reputation, these gravitational giants might be hiding the universe's best-kept secret, portals to realms beyond our wildest imagination. Picture a whirlpool in the ocean, not just pulling ships under, but funneling them into hidden coves on the other side of the world. That's the tantalizing possibility physicists are now exploring, that black holes could be tunnels through space-time, not dead ends. The math behind this idea comes straight from Einstein's equations. When matter collapses into a black hole, it doesn't just vanish. General relativity predicts it forms a singularity, a point where space-time curves infinitely, and the usual rules of physics break down. But here's the twist: some solutions to those equations suggest the singularity might connect to a mirroring structure called a white hole, spewing out matter somewhere else in the cosmos. This cosmic shortcut, known as an Einstein-Rosen bridge or wormhole, could theoretically link distant regions of space, or even different universes entirely. It's like folding a piece of paper so two dots touch instead of traveling the long way across the surface. You punch right through. Of course, there's a catch. The gravitational forces near a black hole singularity are so extreme they'd likely stretch anything entering it into spaghetti-like strands, a process colorfully called spaghettification. But what if some black holes defy this fate? Quantum physics hints that singularities might not be infinitely dense after all. Some theories, like loop quantum gravity, suggest there's a smallest possible unit of space, meaning matter can't collapse endlessly. If true, black holes might compress matter to a critical point, then rebound, creating an exit rather than a doom. Imagine a rubber band stretched to its limit. Instead of snapping, it springs back, launching you into uncharted territory. The most mind-bending part: we might already have evidence of these portals. When astronomers study black holes, some exhibit bizarre behaviors: unexplained jets of particles shooting out at near light speed, or gravitational waves with odd signatures. Could these be echoes of matter emerging elsewhere? Some scientists even speculate dark matter could be ordinary matter that slipped through a black hole's tunnel, forever separated from our universe by the fabric of space-time. Science fiction loves the idea of black hole travel, but the reality could be stranger. A journey through one might not be a scenic ride. Time dilation means you could emerge billions of years in the future, or in a universe where the laws of physics are subtly different. Yet the mere possibility reshapes how we see the cosmos. Black holes might not be graveyards but crossroads, the subway stations of a vast, interconnected multiverse. And if we ever unlock their secrets, the universe's greatest monsters could become its most valuable gateways. Every action, every thought, every event. What if the universe keeps perfect records of it all? This isn't just philosophy. Cutting-edge physics suggests reality might have an unfailing memory, preserving every bit of information like an indestructible ledger. The idea first gained traction when Stephen Hawking proposed that black holes could slowly evaporate, raising a paradox. If a black hole disappears, what happens to all the information it swallowed? For decades, scientists assumed it was lost forever, violating a fundamental law of quantum mechanics that states information can never be destroyed. But what if the universe has a backup system we're only beginning to understand? Imagine tossing a book into a fire. The pages burn, but the ash and smoke still contain traces of the ink. The information isn't gone, just scrambled beyond recognition. Black holes might work the same way. The holographic principle suggests that everything falling into a black hole leaves an imprint on its event horizon, like a fingerprint pressed into cosmic clay. Even as the black hole evaporates, those imprints could remain, encoded in the radiation it emits. In this view, the universe isn't just storing data, it's running a flawless archival system, ensuring nothing is ever truly erased. The implications stretch far beyond black holes. If information is preserved, could the universe itself retain echoes of ancient events? Some theories propose that the cosmic microwave background, the afterglow of the Big Bang, might contain faint traces of long-dead civilizations or collisions between universes. Others suggest that quantum entanglement could weave a hidden network of connections, linking past and present in ways we can't yet detect. Think of it like ripples in a pond. Even after the splash fades, the water never forgets the disturbance. This cosmic memory might even shape the future. The block universe theory, where time is an illusion and past, present, and future coexist, gains new weight if information is eternally preserved. Your choices today could ripple backward as well as forward, woven into the fabric of reality like threads in a timeless tapestry. Ancient cultures spoke of Akashic records, a metaphysical library of all knowledge. Modern physics might be uncovering a scientific counterpart, the most mind-bending possibility. If the universe remembers, could we one day retrieve lost information? Future technologies might decode the holographic imprints on black hole horizons, or reconstruct ancient cosmic events from subtle patterns in spacetime. Time travel could become less about moving through years and more about reading the universe's indelible archives. Whether this memory is passive or active, a silent record or a dynamic force, it hints at a universe far more interconnected and intentional than we ever imagined. The past might not be gone. It might just be waiting to be rediscovered. For over a century, the speed of light has been physics' ultimate constant, a cosmic speed limit etched at 300,000 kilometers per second in the fabric of spacetime itself. But what if this wasn't always the case? Emerging theories propose that light might have raced across the infant universe at breakneck speeds, far exceeding its current pace. This isn't just a tweak to the rules, it's a potential paradigm shift that could unravel mysteries from the Big Bang to the formation of galaxies. The idea first gained traction when cosmologists noticed a puzzling inconsistency. The universe's large-scale structure, the distribution of galaxies and cosmic microwave background shows an eerie uniformity that's hard to explain if light always traveled at its current speed. In the standard model, there wasn't enough time for heat and energy to spread evenly across the cosmos in those first moments. But if light moved faster in the early universe, it could have acted like a cosmic blender, smoothing out temperature differences almost instantaneously. Some models, like the varying speed of light theory proposed by physicist Joe Megiddo, suggest light may have been a staggering 60 orders of magnitude faster seconds after the Big Bang, a fleeting burst of hyperspeed that set the stage for everything we see today. Here's where it gets even stranger. If light speed was variable, it could solve one of physics' greatest puzzles: why gravity and quantum mechanics refuse to play nice. Einstein's relativity depends on light speed being constant, but quantum fields seem to operate on different rules. A universe where light once had flexibility might reconcile these clashes, revealing a deeper layer of physics where the constants we take for granted are actually artifacts of a cooling cosmos. Imagine the laws of physics as a set of Russian dolls. What we perceive as fundamental might just be the outermost layer, hiding a more dynamic past. Evidence for this radical idea is still tentative but tantalizing. Observations of distant quasars, extremely luminous galactic cores, show subtle variations in how light interacts with matter across cosmic time. Some researchers interpret these as fingerprints of a changing speed of light. Even more provocative are anomalies in the fine structure constant, a number that governs how light and matter interact. Measurements from ancient starlight suggest this constant might have been different billions of years ago, hinting that light itself behaved differently. The implications are staggering. A universe with variable light speed could rewrite cosmic history, suggesting that inflation, the rapid expansion thought to have shaped the early cosmos, might not have been necessary. It could also mean that distant regions of space we see as separate were once connected by light's fleeting superhighway, solving the horizon problem that's puzzled astronomers for decades. Beyond cosmology, this idea challenges our very notion of physical laws as fixed and eternal. What if the universe's rules evolved and we're just living in the slow-motion aftermath? Practical applications might sound like science fiction, but they're grounded in real math. If we could harness even a fraction of light's primordial speed, communications across interstellar distances could become near instantaneous. Particle accelerators might unlock energies currently impossible to achieve, probing realms of physics hidden from our sluggish light speed perspective. Most profoundly, a universe where constants vary suggests that physics isn't just about discovering laws. It's about uncovering their origin story. Whether light speed is truly unchanging or a relic of deeper dynamics, one thing is clear: our cosmic rulebook might have footnotes we're only beginning to decipher. The next time you switch on a lamp, consider this: the beam illuminating your room could be the slowed-down descendant of a flash that once lit up the entire universe in an instant. We picture the void between stars as a silent, lifeless expanse, but the universe abhors a true vacuum. Even in the deepest reaches of space, where matter is spread thinner than 1 atom per cubic meter, there's a hidden frenzy of activity. Quantum mechanics reveals that what we call empty space is actually a seething foam of virtual particles, pairs of matter and antimatter, that blink into existence for fleeting instants before annihilating each other. These quantum fluctuations aren't just theoretical. They've been measured in labs through the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a mysterious force pushing them together. The reason: the plates squeeze out some of those virtual particles, creating an imbalance in the quantum froth that generates measurable pressure. This phenomenon points to something astonishing. Space itself crackles with energy even at absolute zero, known as zero-point energy. Calculations suggest the energy density in this quantum vacuum should be enormous enough to boil away oceans in an instant. Yet we don't experience that catastrophic force because most of it cancels out, leaving only faint traces like the Casimir effect. But here's the puzzle. When physicists tally up the energy of these quantum fluctuations, the numbers are off by a staggering factor of 10 to the power of 120 from the observed value of dark energy. This vacuum catastrophe is arguably the worst prediction in the history of science, hinting that we're missing something fundamental about how space stores energy. The implications ripple through both cosmology and future tech. If we could tap even a fraction of this zero-point energy, it might revolutionize space travel. Imagine engines that harness the fabric of space-time itself. Some speculative designs, like the M drive, initially seem to defy conservation of momentum, leading to theories they might interact with this quantum vacuum. While most such claims have been debunked, serious research continues into whether the vacuum's energy could be manipulated. More intriguingly, some theories suggest dark energy, the mysterious force accelerating the universe's expansion, might originate from shifts in this zero-point energy over cosmic time. As the universe grows, its vacuum energy density could be changing in ways we don't yet understand, like a hidden thermostat tweaking the cosmos. What's truly mind-bending is how this reshapes our view of reality. The quantum vacuum isn't passive emptiness, it's an active medium that influences everything from the behavior of atoms to the fate of galaxies. When an electron orbits a nucleus, its path is subtly altered by interactions with virtual particles. Some theories even propose that mass itself arises from particles, dragging through this energetic vacuum, like objects moving through molasses. Ancient philosophers spoke of the ether filling space. Modern physics might have found its quantum counterpart. The next time you gaze at the night sky, remember, the vast darkness isn't empty. It's a cosmic cauldron where particles dance in and out of existence, where the seeds of future technologies might lie hidden, and where the answer to dark energy could be flickering at the edge of perception. The universe's true vacuum isn't silence, it's a whisper of infinite potential. We think of time as an unstoppable river always flowing forward, but what if that's just a local phenomenon? The second law of thermodynamics tells us entropy, the measure of disorder in a system, always increases, creating the arrow of time we experience. Yet the equations of physics work equally well whether time runs forward or backward. This symmetry suggests a startling possibility. Somewhere in the cosmos, time might actually be flowing in reverse. Imagine a mirror universe where cause and effect are flipped, where broken cups reassemble themselves and memories form of events that haven't happened yet. The clues lie in quantum mechanics. In certain experiments, particles seem to decide their properties retroactively, as if future measurements influence past states. This phenomenon, called retrocausality, blurs the line between before and after. Even more bizarre are quantum systems that temporarily decrease in entropy, appearing to defy time's arrow on microscopic scales. While these effects are fleeting, they hint that time's one-way street might not be as absolute as we thought. Some theorists propose that the Big Bang wasn't a unique beginning, but a moment of perfect symmetry, a cosmic pivot where two universes were born, one with time flowing forward and the other backward. This isn't just speculative math. Observations of distant galaxies show matter and antimatter behaving in ways that could suggest time-reversed counterparts. Antimatter particles, often described as regular matter moving backward in time, might be more than a convenient metaphor. The universe's missing antimatter, why matter dominates when both should have been created equally, could be explained if antimatter fell into the past at the moment of creation, populating a mirror universe where time runs the other way. The implications rewrite our understanding of existence. A universe with bidirectional time could mean every event is mirrored somewhere else, with effects preceding causes. Consciousness itself might be tied to entropy's flow, our sense of now, emerging from the brain's constant processing of increasing disorder. If time reversed, would memories unravel? Would stars consume light instead of emitting it? The very fabric of reality might look alien in such a realm. Yet the most profound question isn't whether time could reverse, but whether it already has. The cosmic microwave background shows eerie symmetries that some interpret as collision marks with a time-reversed sibling universe. If true, the arrow of time might not be a universal law, but a local quirk, a cosmic accident that could, under the right conditions, flip direction. Whether time is a river or a pendulum, one thing's certain: our place in its flow is far more mysterious than we ever imagined. What if every sunrise, every breath, every star in the night sky were nothing more than lines of code in an unfathomably advanced simulation? The idea seems ripped from science fiction, but it's a serious hypothesis debated by physicists and philosophers, one that challenges the very nature of existence. Nick Bostrom's seminal simulation argument lays out a chilling trilemma. Either civilizations like ours almost always go extinct before reaching technological maturity, they lose interest in creating ancestor simulations, or we're almost certainly living in one. Given the breakneck pace of our own virtual reality advancements, the third option starts to feel less like paranoia and more like a legitimate possibility. Think of how video games have evolved in just 50 years, from pixelated Pong to sprawling digital worlds with realistic physics and AI-driven characters. Now extrapolate that progress over thousands or millions of years. A civilization slightly more advanced than ours could have the processing power to simulate entire universes, complete with conscious beings who believe their reality is fundamental. The math isn't just plausible, it's startlingly efficient. Creating one real universe requires unimaginable energy, but simulating trillions of minds within a quantum computer might require only a modest energy investment by comparison. From a resource standpoint, simulated realities could outnumber base reality by a factor of billions to one, making the odds overwhelmingly stacked against us being the original. But who would build such a simulation and why? The motivations could range from scientific curiosity, studying historical or evolutionary pathways, to something more existential. Advanced civilizations might create simulations to cheat death, uploading their consciousness into customizable realities. Others could be running ethical stress tests, observing how societies develop under different conditions. The most unsettling possibility: we might be someone's entertainment, a cosmic soap opera playing out for an audience we can't perceive. Ancient myths spoke of gods toying with humanity. Modern science frames the same idea with different vocabulary. Evidence for this hypothesis might already exist in the fabric of reality. Quantum mechanics shows that particles exist in probabilistic states until observed behavior that mirrors how video games render graphics only when a player looks. The universe's pixelated nature, with Planck length and time setting minimum resolutions, could indicate underlying code constraints. Even mathematical constants like pi or the fine structure constant might be parameters set by the programmers. Some researchers search for glitches, unexplained phenomena like quantum entanglements, faster-than-light communication that could reflect optimization shortcuts in the simulation's architecture. The implications rewrite everything. If reality is simulated, concepts like free will, mortality, and meaning take on new dimensions. Are our choices our own or predetermined by algorithms? Is death merely a log-out screen? Religions have long described existence as illusory, from Hindu Maya to Plato's cave, while transhumanists now speculate about jacking out of the simulation entirely. Ethical dilemmas abound. If we're simulations, does our suffering matter? And if we one day create conscious simulations ourselves, do we become gods or prisoners of an infinite regression? Yet the simulation hypothesis isn't without critics. Some argue it's unfalsifiable, a modern creation myth dressed in tech jargon. Others point out that simulating every particle in the universe would require more energy than the universe contains, though proponents counter that shortcuts like procedural generation could reduce computational load. The most poignant rebuttal comes from human experience. Love, art, and discovery feel too vivid to be mere data points, but that itself could be part of the design emotional richness keeping us from questioning our coded confines. Whether metaphor or reality, the simulation hypothesis forces us to confront profound questions about consciousness, purpose, and the nature of reality itself. If we're living in someone else's experiment, the greatest rebellion might be to live so brilliantly that the programmers pause their code to watch. After all, even if this is a simulation, it's the only reality we've got. And that makes it worth exploring, questioning, and embracing to the fullest. Gravity holds entire galaxies together, yet it's so weak that a tiny refrigerator magnet can defy Earth's entire pull on a paperclip. This cosmic contradiction has baffled scientists for decades. How can the force that sculpts the universe be 10 to the power of 39 times weaker than electromagnetism? The answer might lie not in what we can see, but in unseen dimensions folded into the fabric of reality. Imagine our universe as a bedsheet stretched flat. All known forces, electromagnetism, the strong and weak nuclear forces operate on this surface. But gravity could be different. String theory suggests it might leak into extra dimensions curled up so small we never notice them, like water seeping through microscopic pores in the sheet. This would explain its apparent weakness. Most of its strength dissipates into realms beyond our perception. Think of blowing up a balloon with pinholes. No matter how hard you inflate it, air escapes unnoticed. Gravity might behave the same way, its full power diluted across hidden spatial folds. Evidence for this idea comes from bizarre gravitational anomalies. At microscopic scales, experiments show gravity behaves unexpectedly, deviating from Newton's laws. Some interpret this as glimpses of higher dimensions influencing the force we perceive. Even more compelling are calculations showing that if gravity operated solely in our familiar 3 dimensions, black holes would violate quantum mechanics. But when extra dimensions are factored in, the math suddenly works. It's as if the universe has been leaving clues in plain sight, waiting for us to decode them. The implications are staggering. If gravity leaks into extra dimensions, it means our reality is just a slice of something vastly larger, a cosmic iceberg with most of its structure hidden beneath the surface. These hidden dimensions could be compactified, curled into shapes smaller than an atom, or they might extend infinitely, parallel to our own. Some models propose that every particle in our universe has counterparts vibrating in these extra dimensions, like notes played on unseen strings. This wouldn't just explain gravity's weakness, it could unite all fundamental forces under one framework, revealing them as different vibrations of the same multidimensional fabric. Practical applications sound like science fiction, but they're grounded in serious physics. If we could manipulate these extra dimensions, we might one day engineer gravity fields, creating anti-gravity chambers or warp drives that bend spacetime itself. Particle accelerators might produce micro-black holes that wink in and out of existence, offering direct evidence of higher dimensions. The Large Hadron Collider has already searched for such phenomena, and while none have been confirmed yet, the hunt continues. But the most profound implication isn't technological, it's philosophical. If extra dimensions exist, then everything we perceive is just a shadow of deeper reality. Ancient mystics spoke of unseen worlds. Modern physics might be quantifying those very ideas. Gravity's weakness could be our first tangible clue that the universe is far richer, stranger, and more interconnected than our senses suggest. The next time you drop a ball and watch it fall, consider this. You're not just witnessing gravity's pull, but the whisper of hidden dimensions shaping reality itself. The Big Bang is often described as the ultimate beginning, a singular moment when space, time, and matter erupted into existence. But what if that explosive birth was just the latest chapter in an endless cosmic cycle? The Big Bounce theory proposes something radical. Our universe didn't emerge from nothingness, but from the collapse of a previous cosmos. Picture an infinite cosmic heartbeat, expansion and contraction, over and over, with each cycle birthing a new universe from the ashes of the old. This idea isn't just philosophical speculation. It emerges from the math of loop quantum gravity, a leading candidate for unifying quantum mechanics and general relativity. When scientists rewind Einstein's equations toward the Big Bang, they hit a point where gravity becomes so intense that quantum effects take over. Instead of a singularity, a point of infinite density, the equations suggest a quantum rebound. Like a ball compressing to its limit before springing back, the collapsing universe would reach a minimum size, then bounce outward in a new Big Bang. No mysterious creation event required, just physics playing out in an eternal loop. The evidence is still tentative but tantalizing. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that some physicists interpret as echoes of a pre-bounce universe. Certain anomalies in how galaxies cluster could also hint at inherited structures from a previous cycle. Even dark energy, the mysterious force accelerating our universe's expansion, might be a relic of the bounce, a kind of cosmic recoil energy from the last contraction. What's truly mind-bending is how this reshapes our place in the cosmos. If the cycle is endless, there could have been countless universes before ours, each with slightly different physical laws. Some might have been stillborn, collapsing almost immediately. Others could have lasted trillions of years before crunching down again. Over enough cycles, universes with the right conditions for life, like ours, would inevitably emerge through sheer persistence. This isn't just recycling matter, it's recycling possibility itself. Critics argue the theory is untestable, but new breakthroughs are chipping away at that notion. Some models predict that gravitational waves from the bounce might still ripple through our universe, waiting to be detected. Others suggest that black holes could preserve quantum imprints of the previous cycle, like fossils in spacetime. Even if definitive proof remains elusive, the Big Bounce offers something profound, a vision of the cosmos where endings are just beginnings in disguise. The next time you look up at the stars, consider this: you might be gazing at the latest iteration of an infinite story, written and rewritten across eternity. Squeeze your hand against a table. What you feel as solid, unyielding wood is actually a cosmic magic trick. At the atomic level, the particles making up that table are almost entirely empty space. Picture blowing up a hydrogen atom to the size of a football field. At its center, the nucleus would be no larger than a single grain of sand, while the lone electron would whiz around the outermost seats like a frantic spectator. The rest pure void. So why doesn't your hand simply pass through the table like a ghost? The answer lies in forces so subtle they redefine what solid really means. This illusion of solidity comes down to the electromagnetic dance between atoms. Each electron carries a negative charge, creating an invisible force field around every atom. When your hand presses against the table, these fields repel each other with tremendous strength, like trying to push two powerful magnets together at their matching poles. The sensation we interpret as solidity is really just an army of charged particles refusing to overlap. Think of it like a ceiling fan spinning at full speed. While the blades are mostly empty space between metal, try sticking your hand through, and the force feels unmistakably solid. Quantum mechanics adds another layer to this cosmic sleight of hand. Electrons don't orbit nuclei like planets around a sun. They exist as probability clouds, occupying fuzzy regions where their position and momentum are uncertain. These clouds create standing waves of negative charge that act like bumpers in a pinball machine, deflecting incoming atoms. The closer two atoms get, the more their electron clouds distort, generating intense resistance. It's not that atoms physically touch, they negotiate personal space through invisible force fields, like strangers in a crowded elevator maintaining an unspoken barrier. Here's where it gets even stranger. The hardness of materials depends on how these electron clouds arrange themselves. In diamond, carbon atoms lock into a rigid lattice, their electron clouds interlocking like puzzle pieces to create an unyielding structure. In contrast, graphite made of the same carbon atoms feels slippery because its clouds form loose layers that slide past one another. Both are fundamentally empty space, yet their quantum interactions create wildly different experiences of solidity. The most mind-bending implication: if you could magically switch off electromagnetism, every object around you would collapse into an indistinguishable haze of particles. Mountains, skyscrapers, even your own body would dissolve into a diffuse cloud of nuclei drifting through nothingness. The solid world we take for granted isn't just fragile, it's a delicate balance of forces maintaining the grand illusion of permanence. Next time you lean against a wall or take a sip from a glass, remember, you're not interacting with matter so much as negotiating with invisible fields that collectively decide what gets to feel real. Consider the delicate precision of a master watchmaker, every gear, spring, and balance wheel calibrated to within 1,000th of a millimeter. Now imagine that same precision scaled up to cosmic proportions. The universe operates under a set of fundamental constant numbers like the strength of gravity, the speed of light, and the mass of an electron that seem almost impossibly fine-tuned for life to exist. Tweak any one of these values even slightly, and the consequences are catastrophic. If gravity were just a fraction stronger, stars would burn out in millions of years instead of billions, leaving no time for life to evolve. If the electromagnetic force were weaker, atoms couldn't bond to form molecules. Even the density of dark energy appears perfectly balanced too much, and the universe would have torn itself apart before galaxies could form. Too little, and matter would have collapsed back into a cosmic crunch long ago. This razor's edge precision is what physicists call the fine-tuning problem. The odds of all these constants aligning by chance are staggeringly low, like rolling a million-sided die and landing on the exact same number a dozen times in a row. Some researchers calculate the probability at less than 1 in 10 to the power of 200. That's a decimal point followed by 200 zeros before you hit a single digit. Faced with these numbers, scientists have proposed two compelling explanations. Either we've hit the ultimate cosmic lottery, or there's something deeper at work, a principle we don't yet understand that makes life not just possible but inevitable. One fascinating theory is the multiverse hypothesis. If countless universes exist, each with randomly determined constants, it's statistically inevitable that at least one would have the right conditions for life. We just happen to be in that lucky one. Think of it like a vast cosmic casino. While most universes lose and collapse or remain barren, a rare few hit the jackpot. Another possibility is that these constants aren't arbitrary at all, but emerge from a deeper, unified law of nature we haven't discovered yet. The way temperature and pressure arise from the motion of molecules, these constants could be surface-level effects of a hidden quantum fabric. Yet the most profound implication isn't just about physics, it's about meaning. For centuries, philosophers and theologians have argued that fine-tuning suggests intentional design. Modern cosmology reframes that idea without invoking a designer. Some theories propose that consciousness itself could play a role in determining these constants, as if the universe evolves toward conditions that allow observers to exist. Others speculate that life might not be a passive beneficiary of fine-tuning, but an active participant in shaping it. The next time you take a breath or feel sunlight on your skin, remember, you're not just existing in the universe. You're the result of an exquisite, mysterious calibration that's still being decoded. Whether by chance, necessity, or something beyond our current understanding, the cosmos seems rigged in favor of life. And that might be the most astonishing revelation of all. The idea of stepping into a machine and emerging centuries in the past or future has long been the stuff of science fiction, but the equations of general relativity suggest it might not be impossible. Einstein's theory reveals that spacetime isn't a rigid stage. It's more like a stretchy fabric that can warp, twist, and even fold under extreme conditions. And where there are folds, there could be shortcuts, wormholes, hypothetical tunnels connecting distant points in time and space. Picture a piece of paper with two dots drawn far apart. Normally, you'd need to travel the full length of the paper to connect them, but fold the paper and those dots touch. A wormhole would do the same for the cosmos, creating a bridge where time and distance lose their usual meaning. The most plausible candidates for these spacetime tunnels might be lurking inside black holes. Under certain conditions, a black hole's crushing gravity could rip open a passage to another point in spacetime, though surviving the trip is another matter. Quantum physics suggests these tunnels would be unstable, snapping shut faster than light could traverse them. But advanced civilizations might theoretically stabilize them using exotic matter with negative energy, a substance that repels gravity rather than attracting it. While we've never observed such matter, quantum experiments hint that it might exist in tiny amounts, like the fleeting bubbles of negative energy that appear and vanish in the quantum foam of empty space. Even stranger are cosmic strings, hypothetical defects in spacetime left over from the Big Bang, thinner than an atom but stretching across the universe. If two of these strings moved past each other at near light speed, they could warp spacetime so severely that closed time-like curves would form, loops allowing travel to the past. It's like twisting a rubber band until it kinks back on itself. Time, under the right conditions, might do the same. The energy required is beyond anything we can produce, but the math doesn't forbid it. Yet the greatest hurdles aren't just technical, they're logical. Time travel introduces paradoxes that scramble causality. The classic grandfather paradox asks, if you went back and prevented your grandfather from meeting your grandmother, how could you exist to make the trip? Some physicists argue the universe would self-correct, ensuring your actions somehow preserve the timeline. Others propose branching realities, each change spawning a parallel universe where history unfolds differently. Then there's the idea of self-consistent loops where your time travel was always part of history. Imagine finding a time machine in the future, using it to travel back and leaving it where you originally found it, a loop with no beginning or end. Despite these puzzles, time travel might already be happening on microscopic scales. Quantum particles occasionally exhibit behavior that looks like reverse causation, with measurements in the present appearing to influence events in the past. While this doesn't mean humans can hop through time, it suggests the universe's rulebook might be more flexible than we thought. Whether through wormholes, cosmic strings, or some yet undiscovered phenomenon, the fabric of reality might one day yield its most guarded secret, not just how to observe time, but how to navigate it. Galaxies spin so fast they should tear themselves apart, stars flung into the void like riders thrown from a carousel, yet they hold together, bound by something unseen. The culprit, dark matter, an invisible cosmic glue that makes up 85% of the universe's mass, yet leaves no trace beyond its gravitational pull. Picture a city at night, its streets illuminated by street lamps. The lights represent the stars and gas we can see, while the sprawling darkness between them, the neighborhoods, parks, and alleys we can't fully make out, holds most of the city's substance. That's the role dark matter plays on a galactic scale, the hidden infrastructure shaping everything we observe. The evidence for this mysterious substance is overwhelming. When astronomers measure how galaxies rotate, they find the outer stars moving just as fast as those near the center, a direct violation of Newton's laws unless some unseen mass is holding them in place. Even more compelling are observations of galactic collisions like the famous Bullet Cluster. When two galaxy clusters smashed together, their visible gas clouds slowed and heated up, but their gravitational fields, mapped by distorted background light, kept racing ahead as if dragged by something invisible. It's like watching a ghostly hand move through a cloud of smoke, leaving no fingerprints but bending the fabric of reality around it. So what could dark matter actually be? The leading candidates are WIMP, weakly interacting massive particles, hypothetical subatomic particles that barely interact with normal matter except through gravity. Billions might be streaming through your body right now, as intangible as a breeze passing through a screen door. Other theories propose actions, ultra-light particles with exotic quantum properties, or even primordial black holes formed in the universe's first moments. The wildest possibility, dark matter isn't particles at all, but a shadow universe with its own forces and structures, forever hidden from our perception. The hunt for dark matter has spawned some of the most ingenious experiments in science. Deep underground, shielded from cosmic rays, detectors filled with liquid xenon wait for the once in a lifetime collision between a dark matter particle and an atom. In space, telescopes scan for gamma rays that could signal dark matter annihilations. Even particle colliders like the Large Hadron Collider might create dark matter in high-energy crashes, though we'd only infer its presence by missing energy in the aftermath. After decades of searching, we've found nothing, yet that absence is telling us something profound about the nature of reality. The irony is breathtaking. Dark matter shapes the cosmos, sculpting the grandest structures in existence, yet it refuses to reveal itself. Without it, galaxies wouldn't have formed, stars wouldn't ignite, and life as we know it couldn't exist. We're left with a universe where the most fundamental stuff is also the most elusive, a cosmic joke written in gravity's subtle fingerprints. Every time you look at the night sky, remember, what you're seeing is just the glittering surface of a far deeper mystery. Astronomers have uncovered a cosmic speedometer discrepancy that's shaking the foundations of modern physics. When we measure how fast the universe is expanding using nearby galaxies and supernova, we get one number, but when we calculate it based on the afterglow of the Big Bang, we get another. These values should align perfectly, yet they're diverging by nearly 10%, a gap that grows wider with every new observation. It's like checking two identical clocks only to find one ticking faster, forcing us to question whether time itself is broken or if we've misunderstood the machinery of the cosmos entirely. This tension centers around the Hubble constant, the number that describes the universe's expansion rate. One approach uses standard candles like Cepheid variable stars and Type Ia supernova, whose predictable brightness lets us gauge distances to nearby galaxies. These measurements suggest an expansion rate of about 73 kilometers per second per megaparsec. But when scientists analyze the cosmic microwave background, the faint radiation from the universe's infancy, they arrive at 67. At first, researchers dismissed the mismatch as observational error. Yet after decades of refining instruments, from the Hubble Space Telescope to the Planck satellite, the gap refuses to close. The universe isn't just expanding, it's doing so with inexplicable haste. The implications are staggering. If both measurements are correct, our standard model of cosmology, the lambda-CDM framework that's guided physics for decades, might be missing a critical piece. One tantalizing possibility is that dark energy, the mysterious force driving cosmic acceleration, isn't constant as we've assumed, but growing stronger over time. Picture a car where the gas pedal sinks deeper on its own, making the engine roar faster without the driver's input. Alternatively, there could be unknown particles, like a new type of neutrino zooming through space and tweaking the expansion rate. Some theorists even speculate that gravity itself behaves differently on cosmic scales, weakening over vast distances and allowing galaxies to flee faster than predicted. The most radical solution: our universe might have collided with another in the distant past, injecting extra energy that's now manifesting as anomalous expansion. Or the cosmos could be lopsided, with our local neighborhood expanding faster than other regions, skewing measurements like a funhouse mirror. Even more mind-bending is the idea that the fundamental constants of nature, numbers like the speed of light or the strength of gravity, might be slowly evolving, subtly altering the rules of reality over billions of years. Whatever the answer, this puzzle reminds us that the universe still holds profound mysteries. Every time we think we've mapped its boundaries, it reveals new layers of complexity, daring us to look deeper. The next generation of telescopes, like the Vera Rubin Observatory and the James Webb Space Telescope, could finally crack this case or plunge us into even greater uncertainty. One thing's certain, the cosmos is in a hurry and we're racing to keep up. Imagine flipping a coin heads or tails, a clear outcome. But at the quantum level, that coin spins forever, existing as both possibilities simultaneously until someone catches it. This is quantum superposition, the bizarre principle that particles like electrons can occupy multiple states at once, spinning clockwise and counterclockwise, being here and there, until an observation forces them to choose. Schrödinger's famous thought experiment, where a cat in a box is simultaneously alive and dead until someone looks, wasn't just a whimsical metaphor. It was a stark illustration of how profoundly quantum mechanics clashes with our everyday intuition. Take the double-slit experiment, where particles fired at a barrier with two openings create an interference pattern, as if each particle passes through both slits at once. The moment scientists try to measure which slit a particle takes, the interference vanishes, the particle picks a path. This isn't a limitation of our tools, it's a fundamental feature of reality. Superposition suggests that particles don't just lack definite properties before measurement, they genuinely exist in all possible configurations, like a cosmic game of choose your own adventure, where every page is simultaneously being written and read. So how does this translate beyond lab experiments? Consider quantum computing, where bits or qubits leverage superposition to perform calculations at unimaginable speeds. A classical computer checks one path at a time. A quantum machine explores all paths at once. It's like solving a maze by being in every corridor simultaneously. Even nature might exploit this principle. Photosynthesis appears unnervingly efficient because plants could be using superposition to test multiple energy pathways at the same instant, almost as if they're calculating the optimal route for sunlight. But the real mystery lies in the role of observation. Does consciousness truly collapse superposition into a single state, as some interpretations suggest? Or is it simply interaction with the environment that forces particles to commit? The debate rages, but one thing's clear: reality at its most fundamental level is fluid, a tapestry of possibilities waiting to be pinned down. Next time you flip a coin, remember, the universe's smallest building blocks never stop spinning. The night sky holds a terrible irony. Its vastness promises countless civilizations, yet we hear only silence. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the billions of galaxies, each with billions of stars and likely even more planets, the universe should be teeming with life. Statistically, we shouldn't be alone. Yet after decades of listening with radio telescopes and scanning the cosmos for signs of intelligence, we've found nothing but static. This eerie absence forces us to confront unsettling possibilities about our place in the universe. One explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. The terrifying question is whether this filter lies in our past or our future. If it's behind us, like some improbable step in the evolution of complex life, we might be among the rare civilizations that made it through. But if it's ahead, lurking in our technological adolescence, it could mean every civilization reaches a point where it destroys itself, whether through nuclear war, environmental collapse, or unchecked artificial intelligence. The silence of the cosmos might be a warning, a graveyard of civilizations that failed to survive their own potential. Another possibility is that advanced civilizations exist but operate beyond our perception. Imagine ants in a jungle unaware of the highway being built overhead. To a species billions of years more advanced, we might be too primitive to notice, or they might communicate in ways we can't yet detect using neutrino beams, quantum entanglement, or some physics we haven't discovered. Some theorists suggest they've transitioned to digital existence, living in virtual realities that leave no cosmic footprint. Others propose they've harnessed dark matter, rendering their activities invisible to our instruments. Then there's the zoo hypothesis, the idea that Earth is deliberately isolated, a cosmic wildlife preserve where advanced civilizations observe us without interference. It's a modern twist on ancient myths of gods watching from afar. If true, the silence isn't accidental but curated, a galactic prime directive preventing contact until we reach a certain maturity. Alternatively, we might be early arrivals in a young universe. Complex life could require rare conditions like heavy metals forged in generations of stars. We might be among the first, with others still evolving in the distant future. The paradox also challenges our assumptions about what life looks like. We search for radio signals because that's how we communicate, but advanced civilizations might view such technology as primitive, like smoke signals in the age of fiber optics. Their signatures could be all around us, encoded in pulsar emissions, hidden in DNA, or even woven into the fabric of spacetime itself. The absence of evidence isn't evidence of absence. It might just mean we're looking for the wrong things. Perhaps the most haunting answer is that intelligence is self-limiting. Civilizations might inevitably turn inward, consumed by virtual worlds or cultural stagnation, losing interest in exploration. Or they might encounter a universal bottleneck, energy depletion, gamma-ray bursts, or some unforeseen cosmic catastrophe that resets the clock. The silence could be the universe's way of telling us that intelligence is a fleeting spark in the dark. Yet the Fermi paradox isn't just about aliens, it's about us. Are we the inheritors of a lonely cosmos, or is the universe waiting for us to take the next step? Every unanswered signal, every quiet star, is a challenge to look deeper, think broader, and recognize that the greatest mystery might not be out there, but in our ability to survive long enough to solve it. The silence isn't empty, it's a question, and the answer depends on what we do next. A butterfly flaps its wings in Brazil, and weeks later a typhoon forms over the Pacific. This poetic idea, known as the butterfly effect, isn't just a metaphor about small actions having big consequences. It's a fundamental property of chaotic systems, where even the tiniest variation in starting conditions can spiral into wildly different outcomes. Now imagine scaling this principle up to cosmic proportions. The universe itself might be the ultimate chaotic system, where minuscule quantum fluctuations in its infancy set the stage for galaxies, stars, and even life, all hinging on randomness so delicate that the slightest tweak could have rewritten everything. Consider the birth of our solar system. A cloud of gas and dust collapsed under gravity, but its exact shape and motion were influenced by quantum ripples from the Big Bang. If just one atom in that primordial cloud had veered slightly left instead of right, Earth might never have formed, or it could have ended up in a completely different orbit, rendering life impossible. This sensitivity isn't limited to planetary formation. The distribution of matter in the early universe, which led to the cosmic web of galaxies we see today, was seeded by quantum irregularities smaller than a proton. Billions of years later, those microscopic wrinkles dictated whether you'd be born under a starry sky or in a void of eternal darkness. Chaos even governs the cosmos on grander scales. Black holes, those gravitational monsters, form from the deaths of massive stars, but their exact properties depend on infinitesimal differences in the collapsing star's rotation or density. A fraction more spin, and the resulting black hole might have ejected its outer layers as a gamma-ray burst, sterilizing nearby solar systems. A fraction less, and it could have vanished without a trace. The universe's structure, from the largest galaxy clusters to the smallest habitable planets, is a tapestry woven by chaos, yet there's a paradox here. For all its randomness, the universe also exhibits startling order. The laws of physics are precise and consistent, allowing complexity to emerge from chaos. Some scientists propose that what we call laws might actually be statistical inevitabilities, emergent properties of countless chaotic interactions, like the average temperature of a gas emerging from the frenetic motion of molecules. Others suggest that chaos and determinism might coexist, with the universe playing out every possible variation across infinite parallel timelines. The implications stretch beyond astrophysics. If chaos truly underpins cosmic evolution, it means our existence isn't just improbable, it's a fleeting alignment of countless accidents. The same principle applies to human history, technology, even consciousness. One mutation in our ancient ancestors' DNA, one stray asteroid missing Earth, one delayed invention, and the modern world could look utterly different. Chaos isn't just a force of destruction, it's the engine of possibility, turning the universe into a relentless experiment in novelty. So does chaos govern everything? Perhaps not entirely. Even in the most turbulent systems, patterns emerge. Strange attractors in chaos theory create loops of predictability within randomness, like the recurring rhythms of ice ages or the cyclic births and deaths of stars. The universe might be less a runaway train and more a fractal dance, wildly unpredictable in detail, yet beautifully structured in its broad strokes. Whether chaos is the architect or just the scaffolding, one thing's certain: the cosmos thrives on the edge of uncertainty, where every moment is a tipping point into infinite futures. The idea that rocks, planets, or even the cosmos itself might possess some form of consciousness sounds like mysticism, until you consider the hard problems staring neuroscience in the face. How does the lump of gelatinous tissue inside your skull generate the vivid experience of being you? Material science can map neurons firing and chemicals transferring, but no one has explained how those physical processes create subjective awareness. Panpsychism offers a radical solution. Consciousness isn't an emergent property of complex systems like brains. Instead, it's woven into the fabric of reality itself, as fundamental as mass or charge. In this view, every particle, every atom, every star might possess some rudimentary form of experience, with complexity determining its richness. Think of it like temperature. A single molecule doesn't have a temperature, it's just moving, but gather trillions together, and the collective motion manifests as heat. Similarly, panpsychism suggests that while an electron might have an infinitesimal flicker of awareness, billions organized into a nervous system create the symphony of human thought. This isn't just philosophy. Quantum biology reveals particles behaving differently when observed, hinting that consciousness could influence matter at microscopic scales. Even the universe's fine-tuning constants, perfectly calibrated for life, takes on new meaning if reality has an intrinsic tendency toward awareness. The most striking evidence might come from within. When neurons are observed in isolation, they behave just like any other cells. Yet when interconnected, they produce something inexplicable, qualia, the raw sensations of color, sound, or emotion. If consciousness truly emerged from sheer complexity, artificial intelligence should already be self-aware. But no algorithm, no matter how sophisticated, has ever reported feeling anything. This gap suggests awareness might not be computed. It could be a fundamental feature that complex systems tap into, like a radio tuning into pre-existing frequencies. Critics argue panpsychism is untestable, but cutting-edge experiments are probing the boundary between mind and matter. Studies on anesthesia reveal that consciousness doesn't fade gradually. It drops off abruptly at certain thresholds, as if flipping a switch. This aligns with the idea that biological systems don't generate awareness so much as modulate it. Even cosmology offers clues. The universe's structure, filaments of galaxies stretching across voids, resembles neural networks on a cosmic scale. Could the cosmos be self-aware in ways we're too small to perceive? Whether stars think or atoms dream remains unanswered, but the implications are profound. If consciousness is universal, then destroying ecosystems or polluting oceans isn't just ethically wrong. It might be silencing ancient, alien modes of experience. Conversely, reaching out to the cosmos could mean communicating with entities vaster than we can fathom. The night sky might not be a cold void, but a living tapestry of awareness watching itself unfold. And if that's true, then every time you gaze upward, the universe isn't just observing you, it's observing itself. Every second, trillions of ghostly particles stream through your body, silent, weightless, and utterly indifferent to your existence. These are neutrinos, nature's most elusive messengers, born in the hearts of stars and the violent deaths of supernova. Unlike ordinary matter, they barely interact with anything. A neutrino could pass through a light year of lead without slowing down. Yet despite their indifference to us, these spectral particles carry encrypted secrets about the most cataclysmic events in the cosmos and the conditions of the universe mere seconds after the Big Bang. Detecting something that barely exists requires extraordinary ingenuity. Imagine trying to catch smoke with a fishing net. That's the challenge physicists face. The most advanced neutrino observatories, like Japan's Super Kamiokande, use colossal tanks filled with ultra-pure water, buried deep underground to shield from cosmic noise. When a neutrino does, by some astronomical fluke, collide with an atomic nucleus, it creates a faint blue flash called Cherenkov radiation, a ghostly fingerprint in the darkness. These rare interactions reveal astonishing details. When supernova 1987A exploded in a neighboring galaxy, detectors registered 24 neutrinos hours before visible light arrived, proof that these particles escape stellar collapses unimpeded, while light gets tangled in the wreckage. What makes neutrinos truly revolutionary is how they've defied expectations. For decades, scientists assumed they were massless, until observations showed they oscillate, changing between 3 flavors as they travel. This proved they must have some minuscule mass, appending the standard model of particle physics. That tiny mass could hold the key to one of cosmology's biggest puzzles: why the universe is made of matter at all. The Big Bang should have created equal parts matter and antimatter, which would have annihilated each other, leaving nothing but energy. Yet here we are. Neutrinos' peculiar behavior might explain this cosmic favoritism. Their oscillations could have tipped the scales in matter's favor during the universe's first fractions of a second. Beyond rewriting physics textbooks, neutrinos offer a backstage pass to cosmic violence. When a star goes supernova, 99% of its energy erupts as neutrinos, a torrent so intense it can briefly outshine all the stars in the universe combined. These particles preserve a pristine record of the explosion's inner workings, untouched by the chaotic debris that scrambles electromagnetic signals. Future detectors could pinpoint exactly how stars die, or even catch the faint neutrino whisper of dark matter annihilating in the sun's core. Some theories suggest neutrinos themselves might be part of dark matter, an invisible component of the universe slipping through our detectors. The most mind-bending possibility, neutrinos might be time travelers. Their near-light-speed journeys mean they experience time dilation. A few seconds for us could feel like years from their perspective. Some high-energy neutrinos detected on Earth may have originated in events that, from our frame of reference, haven't happened yet. It's as if the universe is sending us letters postmarked from the future. From supernova to the birth of the cosmos, these phantoms carry stories we're only beginning to decode. The next time you feel nothing, remember, you're being bombarded by cosmic history, written in particles so shy they make shadows seem loud. And in their silence, they may hold the answers to everything. Somewhere beyond the stars, hidden behind the veil of our own Milky Way, an invisible force is reeling us in. The Great Attractor, a gravitational anomaly with the mass of tens of thousands of galaxies, is pulling everything in our cosmic neighborhood toward it at over 2 million kilometers per hour. Yet we can't see it. The Milky Way's dense disk of stars and dust blocks our view, leaving this colossal mystery lurking in the shadows like a cosmic puppeteer tugging on unseen strings. What makes this enigma even stranger is its location in what astronomers call the zone of avoidance, a region of the sky obscured by our galaxy's central bulge. It's like trying to study a mountain hidden behind a fog bank. We detect its gravitational influence through the motion of galaxies around us, all flowing toward the same unseen point like leaves caught in a river's current. The sheer scale of this phenomenon is staggering. The Great Attractor's pull spans over 400 million light-years, influencing thousands of galaxies in what's known as the Laniakea supercluster, our home supercluster, a web of galaxies so vast it redefines our place in the cosmos. But here's the twist: the Great Attractor might not be the final destination. Recent observations suggest an even larger structure lies beyond it, the Shapley supercluster, a monstrous congregation of galaxies with gravity so strong it could be the true source of our motion. Imagine a game of cosmic tug-of-war with the Great Attractor as a waypoint rather than the finish line. This raises a chilling possibility. What if we're just one ripple in a cascade of gravitational currents, flowing towards something even more unimaginable? The hunt to unravel this mystery has led to some of the most ingenious workarounds in astronomy. Since visible light can't penetrate the zone of avoidance, scientists use radio telescopes and X-ray observatories to peer through the galactic haze. These tools reveal a chaotic realm of colliding galaxy clusters and swirling dark matter, clues that the Great Attractor might not be a single massive object, but a dense knot in the cosmic web where filaments of dark matter intersect. It's like finding the eye of a storm by tracking the winds around it. The implications stretch beyond mere curiosity. If dark matter, the invisible scaffolding of the universe, is concentrated here, studying the Great Attractor could finally shed light on this elusive substance. Some theories even suggest exotic phenomena at work, like primordial black holes from the Big Bang or quantum defects in spacetime itself. Whatever the answer, one thing is certain: our galaxy isn't drifting aimlessly. It's being summoned, and whatever lies at the end of that gravitational whisper might rewrite our understanding of the universe's grand architecture. So the next time you look up at the Milky Way's glowing band, remember, it's not just a backdrop, it's a curtain, and behind it, something colossal is waiting to be discovered. Whether it's a cosmic anomaly, a hidden supercluster, or something beyond our current physics, the Great Attractor reminds us that even in the vastness of space, we're all part of a motion far greater than ourselves. We take the laws of physics for granted: the speed of light, the strength of gravity, the charge of an electron, as if they were engraved in cosmic stone. But what if these so-called constants are more like cosmic weather, shifting over unimaginable timescales? This isn't just theoretical speculation. When astronomers peer back to the universe's infancy using ancient quasars as time capsules, they find tantalizing hints that the fine structure constant, a number governing how light interacts with matter, might have been slightly different billions of years ago. It's like discovering the rules of chess change the further back you go in history, leaving us to wonder whether we're even playing the same game. The implications are staggering. If physical constants vary, then the universe operates less like a machine with fixed gears and more like an evolving organism, its fundamental rules written in erasable ink. Take the speed of light, the ultimate speed limit anchoring Einstein's relativity. If it were faster in the early universe, as some theories propose, it could explain the eerie uniformity of the cosmic microwave background, the afterglow of the Big Bang. Heat and energy would have had time to spread evenly before space expanded, like ink diffusing instantly in water instead of sluggishly crawling. But this tweak would unravel centuries of physics, forcing us to redraw the cosmic blueprint from scratch. Even gravity might not be immune. Newton saw it as an unchanging force, but modern cosmology suggests its strength could fluctuate across cosmic epochs. Some models propose that dark energy, the mysterious force accelerating the universe's expansion, is actually gravity itself weakening over time. Imagine a spring losing its tension. As gravity's grip loosens, galaxies flee faster from one another. This would mean the universe's fate isn't just about dark energy's push, but gravity's fading pull, a slow-motion unspooling of the cosmic fabric, the most radical idea. These shifts might not be random. Just as temperatures cycle with the seasons, the universe could have epochs where constants oscillate, driven by some deeper, hidden physics. String theory suggests extra dimensions might uncurl during these phases, subtly altering how forces manifest in our reality. It's as if we've been studying shadows on a cave wall, unaware that the light casting them flickers. Critics argue these variations could be measurement errors, but the anomalies persist. When light from distant quasars passes through interstellar clouds, absorption lines reveal subtle differences in how atoms behaved billions of years ago. Some elements appear to have absorbed light at wavelengths that no longer match today's physics, like a piano tuned slightly sharper in the past. Even more provocative are lab experiments with atomic clocks, which show potential fluctuations in fundamental constants over mere years, though the results remain hotly debated. If true, this doesn't just rewrite textbooks, it redefines existence. Life relies on exquisitely balanced constants. Tweak them slightly, and stars wouldn't fuse carbon, molecules wouldn't bond, and complexity would never arise. A universe with drifting constants might be a garden where the soil chemistry changes daily, allowing life to sprout only in fleeting windows of stability. We could be living in one such golden era, oblivious to epochs before or after where physics forbids sentience entirely. The next time you switch on a light or feel gravity's tug, consider this: the rules you depend on might be temporary. The universe could be a shapeshifter, its laws mere habits rather than commandments, and we're just here to witness one fleeting iteration of its infinite metamorphosis. We like to imagine the universe as an endless, featureless expanse, but geometry might have the final say on its true shape. For centuries, mathematicians and physicists have debated whether space is flat like a sheet of paper, curved like a sphere, or twisted into a saddle like hyperboloid. This isn't just abstract theorizing. The universe's geometry governs everything from the fate of galaxies to whether time itself has an expiration date. The key to this cosmic riddle lies in a number called omega, the ratio of the universe's actual matter and energy density to the critical density needed for perfect balance. Imagine a tightrope walker poised between two outcomes. If omega equals 1, space is flat, expanding forever but gradually slowing to a near standstill. If it's greater than 1, the universe curves back on itself like a four-dimensional sphere, destined to collapse in a big crunch. Less than 1, and space forms an infinite saddle shape, stretching into ever-thinning emptiness. For decades, measurements of the cosmic microwave background, the afterglow of the Big Bang, seemed to confirm a flat universe. The patterns of temperature fluctuations matched predictions for perfect Euclidean geometry, where parallel lines never meet or diverge. But here's the catch: this flatness appears unnervingly precise, fine-tuned to 1 part in 10,000 billion. Without some hidden mechanism, such perfection defies probability, like balancing a pencil on its tip for eternity. Recent observations complicate the picture. Dark energy's accelerating push suggests the universe might be ever so slightly saddle-shaped, destined for a big freeze where galaxies vanish over the horizon of perception. Yet gravitational lensing data how massive objects bend light hints at positive curvature, as if we're inside a cosmic bubble. The discrepancy could mean our local geometry is warped by unseen megastructures, like ants on a crumpled sheet unaware of the larger landscape. The most radical possibility: the universe might be finite but boundless, a higher dimensional shape we can't perceive. Picture a Pac-Man screen. Travel far enough in one direction, and you reappear on the opposite side without ever hitting an edge. If space is a 4D hypersphere, a powerful enough telescope could theoretically spot distant galaxies from multiple angles, their light having circumnavigated the cosmos. What's at stake isn't just cartography, but causality. A closed universe might allow time loops where the future influences the past. A saddle-shaped one could spawn parallel realities in its infinite folds. Even the concept of nothingness changes. If space is curved, true emptiness might be mathematically impossible. The universe's shape isn't just about where we're going, but what we fundamentally are: passengers on a geometric journey with no map, only the stars as cryptic signposts. Every solid object you've ever touched, walls, doors, even your own skin, isn't as impenetrable as it seems. At the quantum level, particles perform a magic trick that defies classical physics. They vanish on one side of a barrier and reappear on the other, as if the obstacle wasn't even there. This isn't hypothetical. Quantum tunneling is a well-documented phenomenon where electrons, protons, and even entire atoms exploit the fuzzy edges of reality dictated by Heisenberg's uncertainty principle. Imagine rolling a ball up a hill so steep it should never reach the top, yet occasionally the ball simply appears on the other side without climbing. That's tunneling in action, and it's not just breaking the rules, it's rewriting them. This bizarre behavior stems from the wave-like nature of quantum particles. Unlike classical objects with definite positions, particles exist as probability clouds, regions where they might be found. When such a cloud encounters a barrier, most of it reflects back, but a tiny fraction leaks through to the other side. It's as if the particle's wave function samples every possible path, including the forbidden one, and occasionally finds an opening. The thicker the barrier, the lower the odds, but given enough attempts, the impossible becomes inevitable. In fact, without tunneling, the sun wouldn't shine. Hydrogen nuclei in stellar cores rely on this effect to overcome their mutual repulsion and fuse, releasing the energy that powers stars. Life itself depends on particles cheating the cosmic rulebook. Now, engineers are harnessing this quantum loophole to revolutionize technology. Tunnel diodes, already in use, exploit electron tunneling to create ultra-fast switches for computers and radios. Scanning tunneling microscopes map surfaces atom by atom by measuring how electrons tunnel between a probe and a sample, a technique so precise it can manipulate individual atoms. But the real frontier lies in energy and medicine. Imagine solar panels that absorb a broader spectrum of light by leveraging tunneling to capture low-energy photons that normally pass through. Or cancer treatments where protons tunnel precisely into tumor cells, minimizing damage to healthy tissue. Even nuclear fusion reactors could become viable if we master tunneling to stabilize plasma at lower temperatures. The most speculative and thrilling application, quantum biology. Enzymes in our bodies appear to use tunneling to accelerate chemical reactions by factors of trillions. Protons in DNA might tunnel between strands, potentially causing mutations or facilitating repairs. Some researchers speculate that photosynthesis's near-perfect efficiency relies on tunneling to explore multiple energy pathways simultaneously. If we could mimic these processes, we might design biomachines that operate with nature's uncanny precision. Yet tunneling isn't just a tool, it challenges our perception of reality. If particles ignore barriers, does solidity truly exist, or is it just a statistical illusion at human scales? Philosophers have pondered whether consciousness itself could involve quantum processes tunneling through neural pathways. And in the far future, could macroscopic objects tunnel? Theoretically, yes, though the odds of your entire body tunneling through a wall are astronomically low. But given infinite time in an eternal universe, even the rarest events must occur. Somewhere, somehow, a statue might step off its pedestal. From starlight to superconductors, quantum tunneling whispers a tantalizing truth. The universe is far more permeable than it appears. Every wall, every boundary, every limit we take for granted might just be a suggestion, one that quantum particles politely ignore. As we learn to think like these subatomic rebels, we're not just inventing new technologies, we're learning to see the world as it truly is, a place where the impossible is just a probability waiting to be unlocked. Imagine waking up one day to discover your entire life, your memories, the people you love, even the laws of physics, are nothing more than a fleeting hallucination. This isn't the plot of a dystopian novel. It's the Boltzmann brain paradox, a thought experiment so unsettling it challenges the very foundation of how we perceive reality. The premise is deceptively simple. Given enough time, even the most improbable events must occur. In an infinite universe, random quantum fluctuations could spontaneously assemble a fully formed, self-aware brain, complete with fabricated memories and senses, that exists just long enough to question its own existence before dissolving back into the void. And here's the terrifying twist. Statistically, it's far more likely for such a disembodied consciousness to pop into existence than for an entire ordered universe like ours to arise by chance. So how do we know we're not just Boltzmann brains, momentarily convinced we're real? The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who revolutionized our understanding of entropy. He realized that while the universe tends toward disorder, tiny pockets of order can emerge spontaneously, like a wave briefly cresting in a chaotic sea. Extend this logic across eternity, and eventually, even a fully functional mind could emerge from the noise. Think of shuffling a deck of cards endlessly. Given infinite attempts, the cards will eventually arrange themselves into perfect order, if only for an instant. Now replace the deck with particles and the perfect hand with a conscious observer. The math suggests such aberrations are inevitable over cosmic timescales. But the implications go far beyond abstract probability. If Boltzmann brains are possible, then every observation we make, every scientific law we've painstakingly verified, could be an illusion generated by a disordered cosmos. The stars, the planets, the history books all might be elaborate fabrications of a lone brain's delusion. Even more disturbing is the timescale involved. In a universe destined for heat death, where all energy eventually disperses into cold nothingness, Boltzmann brains would overwhelmingly outnumber real observers like us. After all, it takes far less energy to conjure a single conscious moment than to sustain an entire universe for billions of years. By the numbers, we should be Boltzmann brains. Yet here we are, perceiving consistency and order. Science isn't defenseless against this existential curveball. One escape route lies in cosmology. If the universe is eternally inflating, birthing new pocket universes in an endless multiverse, then stable, ordered realities like ours could be common enough to outweigh fleeting Boltzmann aberrations. Another solution comes from quantum mechanics. Conscious observation might play an active role in stabilizing reality, preventing the chaos that spawns Boltzmann brains. Some interpretations of quantum theory suggest that observers collapse probability waves into concrete events, effectively anchoring reality against random fluctuations. It's as if the universe knows better than to leave its own consistency to chance. Yet the paradox lingers, not as a threat but as a mirror. However unlikely, the Boltzmann brain scenario forces us to confront the nature of existence itself. What makes reality real? Is it the external consistency we observe, or the internal coherence of our experience? Ancient philosophers wrestled with similar questions. Descartes' evil demon, Zhuangzi's butterfly dream, but modern physics gives them razor-sharp teeth. The difference is that we now have tools to test these ideas. The cosmic microwave background's uniformity, the persistence of physical laws across billions of light years. These aren't things a Boltzmann brain's hallucination could plausibly sustain. Reality, it seems, has receipts. Perhaps the most profound takeaway isn't about skepticism, but gratitude. The Boltzmann brain paradox underscores how astonishing it is that we find ourselves in a universe where order persists, where memories align with evidence, and where the question, are we real, has no easy answer. In the end, the paradox may say less about the nature of reality and more about the limits of probability when confronted with consciousness. After all, if a hallucinating brain could reason this clearly, wouldn't that make the hallucination just as valid as real existence? The universe, it seems, enjoys keeping its deepest mysteries one thought experiment away from unraveling everything or nothing at all. What if the universe isn't just described by math? What if it is math? This audacious idea, championed by thinkers like Max Tegmark, proposes that reality isn't merely governed by numbers and equations but is fundamentally made of them. Not just the laws, but the very fabric of existence. Every star, every thought, even your perception of this sentence, might be a mathematical structure playing out in an abstract space beyond space. Imagine flipping through a textbook and realizing the formulas aren't explaining the world, they are the world, and you're just a pattern within them. The evidence starts with an eerie observation. Mathematics works unreasonably well at describing the cosmos. When Einstein scribbled down the curvature of space-time, or Dirac predicted antimatter from pure equations before anyone observed it, it wasn't just accurate, it felt like uncovering a hidden blueprint. Even the most abstract math, like group theory or imaginary numbers, later turns out to mirror physical phenomena with uncanny precision. It's as if the universe isn't just following rules, it's built from them. Tegmark's mathematical universe hypothesis takes this further. Every self-consistent mathematical structure corresponds to a physical reality somewhere. Our universe isn't special, it's just one of countless possible equations running in the cosmic background. But what does it mean to be math? Think of a video game. The world you see, the trees, the weather, the characters, isn't made of pixels so much as it's made of logic. Underneath the graphics, there's only code, if-then statements and variables interacting. In this view, our universe operates the same way. Particles aren't tiny billiard balls but solutions to wave equations. Gravity isn't a force but a geometric property of an equation we call spacetime. Even consciousness could be an algorithm running on the wetware of the brain, a computation in the grand cosmic program. The implications are staggering. If true, it means the search for a theory of everything isn't about discovering laws. It's about identifying which mathematical structure we're inhabiting. Some physicists speculate this could be a Clifford algebra or a particular symmetry group. Others wonder if our universe is a neural network training itself, or a cellular automaton like Conway's Game of Life, where simple rules give rise to unfathomable complexity. The most radical take: there's no outside to this structure, no external simulator or programmer, just the math, existing necessarily, eternally. Skeptics push back. If everything is math, why does it feel like something to be alive? How do squiggles on a page generate the warmth of sunlight or the taste of strawberries? This is the hard problem of consciousness dialed up to 11. One provocative answer is that subjective experience is a mathematical property, an intrinsic feature of certain information processing systems. Just as a triangle's angles always sum to 180 degrees, maybe self-awareness emerges unavoidably in sufficiently complex computations. Practical tests might exist. If the universe is mathematical, its structure should leave fingerprints in the fabric of reality. Some scientists search for unnatural precision in physical constants, digits of pi or Fibonacci sequences hidden in the cosmic microwave background. Others look for computational limits, like a minimum length or time interval, hinting at underlying discrete math. Even quantum indeterminacy could be a feature of the universe's rendering engine, approximating continuous reality, the way video games use pixels to mimic smooth motion. Yet the most profound consequence isn't scientific, it's philosophical. If reality is math, then existence isn't a brute fact but a necessary truth. 2 + 2 = 4 didn't start being true when humans invented numbers, it just is. Similarly, our universe might not need a creator. It simply exists because its equation is consistent. Ancient mystics spoke of reality as illusion. Modern physics recasts that illusion as an eternal, intangible pattern. So the next time you solve an equation or count your steps, consider this. You might not be using math, you might be living it, a fleeting configuration in an infinite, immutable landscape of abstract truth. The universe isn't written in the language of mathematics. It is the language, and we're the syllables momentarily given form. From holographic realities whispering that our universe might be a cosmic projection, to the eerie possibility that consciousness itself could be woven into the fabric of space-time, each of these 30 revelations cracks open a door to a reality far stranger than our ancestors ever dreamed. We've wandered through black holes that might be gateways, grappled with dark matter's invisible grip, and even questioned whether time itself is nothing more than an illusion. The deeper we dig, the more the universe seems to revel in shaking our assumptions, leaving us with more questions than answers. Think about the implications. If the holographic principle is true, then every star, every planet, even the device you're holding right now might be nothing more than information painted on the edge of existence. If quantum entanglement links particles across vast distances as if space and time don't matter, what does that say about the true nature of connection? And if the multiverse is real, then somewhere out there, another version of you might be living a life shaped by choices you didn't make. These aren't just abstract thought experiments, they're clues that reality is far more fluid, more mysterious, and more astonishing than we've been taught. Yet the most humbling realization isn't just how much we've discovered, it's how much we haven't. Dark matter and dark energy make up 95% of the universe, and we still don't know what they are. The fine-tuning of physical constants suggests either an unimaginable cosmic coincidence or a deeper principle we've yet to uncover. Even the laws we take for granted might not be fixed, but shifting subtly over billions of years. The universe isn't just hiding its secrets, it's daring us to look closer. So, which revelation shook you the most? Was it the idea that time might not flow at all, but exist as a frozen block where past, present, and future are equally real? Or the spine-tingling possibility that we're living in a simulation, with some advanced civilization running our reality as a cosmic experiment? Maybe it was the quieter, more profound realization that the atoms in your body were forged in the hearts of dying stars, that you are, quite literally, stardust thinking about itself. The journey doesn't end here. Every unanswered question is an invitation to keep exploring, to keep questioning. Because the universe's greatest mysteries aren't locked away in some distant galaxy. They're all around us, hidden in plain sight, waiting for the next curious mind to uncover them. So stay curious, keep looking up, and never stop wondering. And if these ideas sparked your imagination, let's keep the conversation going. Drop a comment below, share this video with fellow cosmic explorers, and don't forget to subscribe for more deep dives into the universe's endless enigmas. The next revelation might be just around the